In this video, I'm going to be taking you through how to make the Lewis structure from the Guide to Lewis Structures. So I'll be going through this in video form for those of you who can learn more easily from that. So again, this will be working with the formula CF4. And we'll need to figure out how we'll set up our Lewis structure based on that formula. First step that we talked about is finding the central atom. And in this case, from our formula CF4, there are several things that we'll need to consider. First is that carbon comes first in the formula name, which is going to be a kind of indication that it's more likely to be the central atom. We also see that we have only one carbon atom while we have multiple fluorine atoms, which is another vote for carbon. The fact that we have multiple fluorines is a vote against the fluorines. One last factor is that this chemical contains carbon, which is often found as a central atom. We do not have any hydrogen in this molecule, so that will not be a factor here, but if we had, we would know that hydrogen is not going to be the central atom. So with these four factors considered, we see that we have 3 votes in favor of carbon, none in favor of fluorine, so we are going to take carbon to be our central atom. In our next step, we can go ahead and set this up as our structure, showing carbon at the center, and then fluorines shown around it. We have 4 fluorines, so we show 4 fluorines around that single carbon. At this point, we've accounted for all of the atoms in the formula. Now that we have all the atoms shown, we need to take stock of the number of electrons that we're going to be dealing with. Remember that in Lewis structures, we are only focused on the valence electrons, so we'll need to think about how many valence electrons are contributed by each atom, and therefore how many we have as a whole. In the case of carbon, we can look to the periodic table and use what we know about electron configuration to find that carbon, as a neutral atom, has 4 valence electrons. And because there's only one carbon atom there, that one carbon atom will bring 4 electrons, and we'll have a total of 4 from the carbon. For fluorine, the periodic table tells us that it's going to have 7 valence electrons, as shown by the fact that it's a halogen in group 17. This time, though, there are 4 fluorine atoms, each of them bringing 7 valence electrons, so we have a total of 28 valence electrons from the fluorines. Altogether, this means that we have a total of 32 valence electrons, which we get by adding the 2 totals shown on the right. Now that we have our total number of valence electrons to work with, we can start adding them to the diagram. Our best place to start is with connecting the central atom to each of the outer atoms, or each of the peripheral atoms. We do that with a single bond, and so I'll show carbon with a single bond to each of the fluorines to show the fact that each of these atoms is actually connected together to make a single unit, a molecule. In doing so, I've shown 4 bonds, and remember that each of these bonds, each of these lines, represents 2 electrons that are being shared between the atoms, a pair of shared electrons. Because we have 4 bonds shown, that's a total of 4 times 2, or 8 electrons that we have accounted for so far, leaving us with 24 electrons to add to the diagram. The remaining electrons will be added as lone pairs. Remember that these are the unshared pairs of electrons, electrons that belong solely to one atom. When adding the lone pairs to a molecule like this, we need to think about which atom we should add to first. And we have 2 major choices, whether we add to carbon first or fluorine first. The rule that we're going to use to justify this is based on the periodic table. We're not fully going to justify it at this point, but in chemistry you'll see where this rule comes from. It tells us that we want to start with the element closest to the top right. And in this case, that's going to be fluorine. Fluorine is closer to the top right of the periodic table than carbon is. So I'll start with the fluorine over on the right side here. I need to figure out how many lone pairs to add to each fluorine. To do so, we use the octet rule, which is based off of what we saw in electron configuration. Noble gases, which have the most stable electron configurations, tend to have 8 valence electrons. And Lewis structures help us to show these atoms becoming more noble gas-like. They are each going to want to have an octet, meaning 8 valence electrons around them, to look like noble gases do. Considering what the fluorine has to start with, it has one bond shown to it, this bond between the carbon and the fluorine. That's a total of 2 electrons. It needs 6 more to get to a total of 8, so we will add those as lone pairs, where these dots, these pairs of dots, represent lone pairs. So we can see this fluorine now has 2 electrons from the bond, and then 4, 6, 8, counting those other 3 pairs of unshared electrons, those lone pairs, and so the fluorine has its octet now. We'll do the same thing with each of the other fluorines, because they are all very similar, each one with one bond to the carbon, and so each one needs 3 lone pairs to get up to the total of 8 valence electrons around it, or to put it the other way, its octet. Again, we'll keep track of what we've done so far. We added 6 electrons, 6 more electrons to each fluorine, and we did that 4 times, so that's a total of 24 that we just added, meaning at this point we're out of electrons. We have added them all to the diagram. What we should be thinking about now is we've added all the electrons that we have available. We need to make sure that this is a good Lewis structure. If it is, then we're done. If not, then we'll have to rearrange things to make it into a better Lewis structure. The way that we check for it being a good Lewis structure is by a double check method. First off, we check to make sure that we have added the correct number of electrons. We've tracked this already, but if we were to go through and count up all the electrons again, we would get a total of 32, which is how many we want. So this passes our first check, correct total number of electrons. We also want to check that each atom has an octet. We've checked the fluorines when we were adding the lone pairs, but we could check again, seeing that, for instance, this fluorine has 2 from the bond, 4, 6, 8, including the lone pairs, so it has its 8, and each of the other fluorines would be counted very similarly. We have not yet checked the carbon, and so we should do that as well. We see that the carbon has a total of 1, 2, 3, 4 bonds shown to it. And because each of those bonds is 2 electrons, we actually do have 8 electrons here, 4 times 2. So the carbon and fluorine each achieved their octets, but they did so in different ways. So since each atom here has the correct number of electrons, in this case octets for both, it passes that check as well. This means that we have found a good Lewis structure for our molecule and are done at this point.